So I'm just going to recap.
I think you have to share the screen also.
I will. Let me just pull up the slide, the PDF of the slides, and then I'll share screen. Okay. So we're covering logistic regression. I did post these also on the Blackboard before coming here. Let me just see. Get to where I want to start. I'll try to do the cost function afterwards, after I show you the MATLAB code. Right, so this is the model. So the equation up above, that sigmoid function, X is your data, W is your model, basically. W is a vector of weights that you are looking to optimize. And essentially, if your model is good, then for every X that comes from the class Y equals 1, this probability will evaluate to a probability above 0.5. And for every X that comes from the negative class, the Y is equal to 0 class, that number will evaluate, that function will evaluate to a number as, less than 0.5, as close to 0 as possible. And I remember that I told you that beware of, I should have this ready. Beware of overfitting with as all of your predictions being close to 1 or close to 0. Okay, so let me actually sit down because I'm going to be, so we're going to make use of another built-in MATLAB data set here. And it's called the cancer data set. We'll clear everything. Okay. I think if you do help cancer data set, it should tell you something. Actually, the contributors of this data set did a really nice job of providing documentation. So, right. So this is your classic benign versus malignant binary classification problem. And so we have 9 features and we have 699 examples. So we have data from almost 700 biopsies, and the excised tissue has been measured for different attributes, such as the thickness of the clump. Some of these, I think, have to be subjective: the uniformity of cell size, uniformity of the shape. And as I'll say many times, I am not a biologist, so you will know more about these features on a biological level than me. So those are the inputs. Inputs are features. That's your X. So your X matrix is going to be 9 by 699. So 9 features, 699 examples. And your targets now, and this is standard, you could represent target with just a single number, but there's a reason why now it's very common to actually have 2 numbers for every example. And that's because sometimes, like here is going to be either, you're going to have, well, we can just print it out.
data set is one of the MATLAB data sets?
Yep. It's also there's a famous machine learning repository, which I'll try to navigate to here, hosted by the University of California of Irvine in Irvine. And many of the data, there's many data sets here. So if you're looking for data sets for your project, you can look at this. So this is the University of California of Irvine. They have this big repository of data, but it also comes in MATLAB. So this is not something like, notice that this file, cancerdataset.mat, is not in my path. Like it is in my path, but it's in the path that comes in with MATLAB installed. The installer put this file on my computer. So you do not actually have to download this yourself. If you have to work with MATLAB, and you have the data already. So I'm gonna load this.
Yeah, that's why I asked, because I can't go.
Oh, you don't have it? Okay, let me just upload it then. Wonder if Finder will find it. It may not, because it's in the it's probably somewhere in the applications.
Does it come with like an add-on to MATLAB instead of like MATLAB?
No, let me just, I think what I'll do is, here. Some hacker's gonna watch this on YouTube one day and hack into my Blackboard. Very what? Okay. I'll just, I guess, let me see. Do you guys all have access to the Blackboard where you are right now? Okay. I mean, we can. You can do this probably with any data. Where is it? So hopefully, give you guys a second. This is my copy. I guess the one thing I'll say about these template data sets, and like another, there's some really famous ones from handwritten digital recognition. They are generally very clean and easy data sets to get good performance on. So in practice, I've never worked with anything like, I've never worked with anything that was as separate, as separable in the feature space as these data sets, but they are really good. They're good when, let's say you want to test out your own algorithm, like you develop something, code something from scratch and you want to test it. It's good to run it on something like this. It's good to run it. And actually what I always do is I train and test on the same thing to at least see that the training performance is good, because then I know that I found the structure in the data, and without worrying about generalization or anything like that. Okay, so my X is going to be the transpose of the input. So MATLAB's logistic regression function, which I'll show you in a second, requires the data to be stored in a format that's examples on the row dimension and features in the column dimension. That's pretty standard, by the way. And the other thing that's kind of annoying about MATLAB's, all of MATLAB's machine learning APIs, like the labels to start with 1, and which is super lame. And so let me just focus on the product. So I'm going to execute these. Scroll up here. Now I can see that X is my feature matrix, and I can visualize it as an image. Right, so here rows are my examples and columns are the features. So every row here is a biopsy. And Y is, well, the way you can look at the unique values of Y.
Are they 1 and 2 instead of 0 and 1?
Yeah, because MATLAB's annoying. Sorry, MATLAB CEO, MathWorks CEO, I'll cut that out of the podcast. No, it's because I guess the rationale is MATLAB is indexed from 1, and I guess they wanted to preserve that all the way. But so let's actually look at cancer targets for the first 5 examples, just to show you. Oops. I guess. Right. So cancer targets. So like the first 3 are benign. The 4th is malignant. The 5th is benign. So you can interpret these as probabilities. So the first row, like for the first 10, if you wanted to look at, right? What this means is that the first biopsy, which is the first column in the data that's presented to us, has a probability of 1 of being benign and the probability of 0 of being malignant. And notice these are all, for this data set, these are all going to be just 1 and 0 because we're certain this is biopsy data. But there are cases, and again, this happens a lot in practice, where you collect some data and you're not 100% confident. What people do, and this is called label smoothing, is that they'll say something like, instead of 1, 0, they'll go like 0.8 and 0.2. And that's a way of telling the learning algorithm that, listen, I'm not exactly sure that this is benign. So it is possible to do that. And actually, why don't we try doing that afterwards as an exercise? See what happens when we put these soft labels on. All right. So step 1 in any kind of working with any data set is just to curate your data into the form required by your fitting function. So you will have to read the documentation of the function that you want to use. So our first function for learning is going to be mnrfit. mnrfit stands for multinomial regression. And so logistic is binomial, but this function lets you have multiple classes. So if you had more than just 2 classes, you could fit a model based on that. And I've used this function actually for something called ordinal logistic regression, which is where if you have multiple classes, like let's say you want to predict survey ratings, and the surveys is like very dissatisfied, moderately dissatisfied, all the way through highly satisfied. That's a 5-class problem, but there's an ordering among the 5 responses, and so that's called an ordinal regression problem. So this lets you do that, which is pretty cool. So you'll always, whether you're working in MATLAB or Python, you'll always want to read the documentation for your fitting function. So mnrfit requires at least 2 arguments, X and Y, and it outputs at least one variable. outputs at least B. So B is going to be your model, your coefficient. So B here is going to be the W in the slides, in the PDFs, in the equations that I was showing you. And so this is something that you will have to do for every function they ever want to use. You're going to have to familiarize yourself with the documentation so you know that you're calling the function right. So we scroll down to X, and X is an n by P matrix. So N is the observation dimension, that's our row dimension, and P is predictor, or another word is feature. So there's also an important notice here is that oftentimes you'll want to include a scalar offset in your model, so intercept term, and sometimes the function will automatically add that in for you, as is the case here. Sometimes it won't. So make sure, don't add it in, because if you add it in and it adds it in, then all of a sudden your data is rank deficient. And you get, if you ever want to like do any kind of an inverse, if there's an matrix inverse involved, which there usually is, you're going to get a singular matrix. So here we're not going to include a column of ones in our features. If you did include a column of ones, it would allow you to model. Basically, it's like your last feature is now just number one. Anything multiplied by one is that number, and so that number becomes your scalar intercept term. It's like the B in y equals mx plus b in the linear regression. Okay, and then it tells you the y is your response value. So again, there's many different names for this. Sometimes it's called the target, sometimes it's called the label. MathWorks calls it the response. And so it tells you that y can be either an n by 1 column vector or an n by k matrix. N by k matrix is, you have for every element, you have a set of k values, one for each class. So in this case, we have two classes. So we are the y that we're putting into mnrfit is going to be 699 by 2. But MathWorks is always very flexible. If you just want to put in one label for each example, that's fine. They'll let you do it. But this is the key. The values have to be from one. When you put in the scalars, they have to be ordered from 1 to k. So you can't put in zeros and ones. You have to put in ones and twos, which is why I did what I did there. Then we're not going to use this feature, but this option. But MATLAB lets you, again, there's different options in this function. Basically, it lets you fit different models, different classes of models. So we're looking for just a standard logistic regression, and we do not need to, that's like the default here. And so here you're choosing between a nominal, ordinal, or hierarchical model. So nominal just means that you have two classes and like the 1 and the 2 don't mean anything, which is the case here. Because like if you called benign 1 and malignant 2, or benign 2, malignant 1, and there's no difference to us. But sometimes if you had 1, 2, 3, and maybe you had benign, uncertain, malignant, then there would be an ordering, and then you would probably want to use, you may want to use the ordinal option. I've never used hierarchical models, but I know they're out there. I know people do them, but I've never used them. The link function, we'll get into link functions later. This is essentially what specifies the form of your model. So this is the log odds that we're using as the default. Logit, I don't know what logit stands for. I always think of it as the log odds. So gamma here is the probability that your example belongs to class 1. And basically the logistic model, as you saw last on Monday, is that the log odds in a logistic model are modeled as a linear function of your data. This is the key, right? We saw that the ratio of the two probabilities, class 1 or class 1 to class 0, is modeled as a linear function of your data. So the bigger this number is, the higher the probability of belonging to the y equals 1 class. And then there's going to be a whole bunch of other. So all we care about in this demo is just our coefficient estimates. So this is our model. We're not going to have interactions. Interaction would be if among those 9, like we're just going to get 9 numbers, 1 weight for each of those biopsy measurements. But you could do things like, let's say that we think the clump thickness interacts with cell size uniformity. And we may want to have an interaction term where basically you're looking to see whether the product of those two predicts benign or malignant. And then there's like, when you're writing a paper, you need statistics. You need like confidence intervals. You need estimates of variability, and this function gives you all that. Okay. This is a classic algorithm. So let's go ahead. So now that I have my data in the form that MATLAB likes, notice that I've taken the second row of cancer targets. I've transposed it to make it features examples by feature, and I've added 1 to it, because if I just do this, I'll have 0s and 1s, and MATLAB lets you get away with murder. It lets you add a scalar to a vector. And actually they've become more flexible. Now you can do things like add a row vector to a column vector, and they'll produce a matrix from that, which is sometimes very bad because it doesn't give you it doesn't error out. And so you think your code is running, but actually it's running, but not in the way that you anticipated, because you meant to add vectors, but instead you've created a matrix. But nevertheless, MathWorks is super flexible. So here you're adding a scalar to a vector, and that's perfectly fine for MATLAB. It just now creates 1s and 2s from 0s and 1s. All right, training. I'm going to run it, and let's evaluate. First of all, let's look at the size of B. It's 10 by 1. Let me just make sure. I always get confused as to, I think the offset for MATLAB is the first parameter. Let me just go back to the help file.
Is that our W0 in the form?
Yeah, so in the PDF, I wrote it like, you could write this as so you could write this as WTX plus W0. Pardon the sloppy here. But what I've done is I've done what is commonly assumed, which is that your X vector already has the last element of every X is a 1. And so then it's just this, and X here, X already contains a 1 at the end or beginning. And so now basically this W here at the top would be 9-dimensional, and this is your 10th parameter. And this W here is already 10-dimensional because your X has been supplemented with this intercept, with this constant. Okay, so I was trying to see whether it's the first value of B or the last that is the intercept. Right. So the first, this is actually, I remember reading this before and being confused. The first K minus 1 rows of B correspond to intercept terms. So for us, K is 2. So just the first value of B, this is the intercept term. But you know what? Oftentimes you don't even need to know how to use, like, to make a prediction. So here I fitted a model. So I figured out the best parameters to map X to Y. there's always going to be a second function. Here it's called mnrval. Oftentimes this function is called predict or test. Like in Python, it's the corresponding, it's called fit. And this is where you actually use the model to make predictions. Here we are predicting same data used for training for the sake of this instructive example. So you would, this will be training performance, but and I'll explain. So again, I'm not, you want to always look at the documentation. And so notice that the MNR val function takes two arguments, but now the first argument is a model, right? So the key thing is, and this is like standard, every tool you'll use, you'll always need to pass in, when you're testing data, when you're making predictions, you won't put an X and Y, you'll put in a model and an X, right? And then the output is your estimate of Y. So pi hat is, pi is probability, so and hat is estimate, so it's an probability. Waiting for the projector to come back on. Oh, let me actually take this minute to plug in my. Good. Paid so much money for this machine, and literally from the first day I got it, it's had a hard time A, charging, and B, keeping it charged, because they made the screen large. It's a large screen and a super high resolution screen, and it just cannot it can't handle working off the battery if you're doing anything intensive. And yeah, no, Zoom is very, especially here I'm recording, sharing, and projecting, and MATLAB. Like, for example, my battery's not charging because this is weird. Let me actually see if I can change my screen brightness. There it is. But still, like, don't sell a laptop that can't charge when it's connected to the power. I pretend I didn't hear that.
My battery lasts like maybe 45 minutes. I'm actually using it. Terrible. I will not turn this for a battery. The newest trade, like it's not even I guess you like you did well. Like PCs aren't depending like on errors, for example. Very, very better. They don't even have fans. She doesn't charge her day. And she uses it all day. Yeah, that will. It is funny though. I watched Can't Last the Entire
Oh, it's still recording? I think it is.
Yeah, so
I do, yeah. When I do that. You can use, I learned the whole procedure.
All right. Let's try to let's try to continue here. If wrapper, oh, it should be fine. I don't know. Let me okay. So we have our model B from the fit function, and now I've converted those. I've passed in B and X into the MNR val function, which is the testing function. So this is going to output pi hat. So let's look at the size of pi hat. It's going to be 699 by 2. And let's look at the first, let's say 10 rows of it. And you see that it looks very confident, right? So it's very confident that the first 3 examples belong to the benign class, and that the 4th example belongs to the malignant class. And so here's a line of code where I'm trying to get just a scalar prediction. I don't want 2 probabilities. I just want to make a hard decision now as to whether y is equal to 1 or 2, 1 for benign, 2 for malignant. So this is the MATLAB's max function. So I'm taking the max of matrix pi hat. And this notation means that I'm taking the max along the 2nd dimension. Why am I doing? The 2nd dimension is my column dimension. Rows is dimension 1, columns dimension 2. So what it means that I'm taking the max of each row. So I'm just picking whichever value is bigger, and I'm assigning that into y hat. So what I'm gonna do is let's see if I can make it. I love these tables. So here's an example. The line of code that I executed is this, which I'll put in the okay, so right, so this is what my table looks like, and you can see that in every for every row, my y hat corresponds to whichever class had the higher probability. So this is just an estimate at this point. Oh, come on. You kidding me? I need to hold it. Okay.
So in the y hat table, now the ones and twos, but the ones are originally zeros.
Yeah, but we did convert them into, so the y, remember I added a 1 to it to make it 1 and 2. So I can just use that y here to evaluate. So what I'm going to do, actually, let me show you that we're going to be okay. Let's print out y as well. So we have, so this is the output of the MNR val. This is our estimate, our hard decision. This is called the soft decision. This is called a hard decision. This is the ground truth. And you see that one is benign. Yeah, one is benign here. Because when I defined it, I took the 2nd row, which is malignant, and I added a 1 to it. So I added, so when this is 0, when cancer targets is 0, y becomes 1. When cancer targets is 1, which is their coding for malignant, y becomes 2. It's a pain. It's a pain. This is standard. You're always grabbing data from somewhere else, and so you often have to recode your labels. Okay, now we're going to calculate the accuracy. So this is the mean. So this is going to be a Boolean vector, right? So y is a number, either 1 or 2, and y hat is a number either 1 or 2. And so this is going to be a Boolean expression, true or false, or logical, as MATLAB calls it. And I'm going to take the mean of it. So MATLAB lets you take the mean, Python 2, you take the mean of Booleans. And my accuracy is 96.8% on the training set, right? So it means that, yeah, it's super accurate, but it's not test data. But it's still good because, I mean, one thing that I look at is we had how many examples did you have and how many features. So here we had 700 examples and 9 features. And so I would argue that even though this is training data, the fact that you could get a 97% accuracy over a sample of 700 examples from only 9 features is pretty good, right? It tells you that there is, like if it was the other way around, if you had 699 features and 9 examples, obviously, then it's like you're over-determined, you're overfitting. But this is a good sign. So this is like probably the first thing you do. What I'm going to show you is I'm going to show you an ROC curve, even though I haven't presented it on a slide yet. This is going to be, so perf curve is a function that comes with the probably statistics toolbox. And it has, if you do help perf curve, tells you that it likes to see 3 arguments. Oh boy. And the arguments are labels, scores, and positive class. So labels is ground truth. Scores, and again, there's so many name terms for the same thing in machine learning. Scores is like the output of your class, the soft output of your classifier. So not an estimate of y. It's the estimate of y before passing it to the nonlinearity that makes it discrete. Pos class is which of the classes are you calling the positive, right? So remember, you have true positives, false positive. So the positive, MATLAB, this function wants to know whether the benign is the positive, the malignant is the positive. And I'm going to call the malignant the positive class here, but it's interchangeable. And I'm going to take the outputs of this perf curve function, and I'm going to plot X and Y. So I'm going to show you what this looks like first. Okay. Yeah. So this is called the ROC curve, stands for receiver operating characteristic. The name it's a legacy name because it comes from like war times when there was a sender and a transmitter and a receiver. But the essential idea is that you can measure the accuracy or the performance of your classifier with a single number if you want. You can say it's 96.8% accurate. However, that is ignoring a lot of information because the 96.8% accuracy was calculated with a threshold of a threshold probability of 0.5. And so what we basically did is when we did this operation here, we looked for whichever probability was higher. So the sum of the probabilities has to equal to 1. And so that's equivalent to going with the prediction that is above 0.5, right? However, we may not want to do that in practice. In practice, we may want to say, I'm going to call anything above 0.25 as malignant, because I want to be sure that nobody walks out of the clinic with a malignant tumor with a negative diagnosis. And so what this curve does is it basically does that, except that it sweeps through all possible thresholds. It sweeps at from a threshold of 0.01 all the way through to 0.99. And so, for example, let's take this end of the curve. So a very low false positive rate means that there were no benign tumors that were classified as malignant. So classified as malignant, you have to be above the threshold, right? So let's say it's 0.25. So so each of these points here is marked. This is a dimensional plot. So every point here corresponds to two numbers: false positive rate and true positive rate. A grade classifier is one that has a true positive rate that's high and a false positive rate that's low, right? So you want to be up here. You want to get to 1 as quickly as possible, essentially. And so you can have a low false positive rate by making your threshold very large. So if you set your threshold to 0.99, you're not going to get any false positives, but you're not going to have positive period. Other hand, if you set your threshold to 0.01, you're going to get a lot of false positives, but you're also going to catch every true positive. And so the key, this is like you're trading off specificity and sensitivity. And so this curve is doing that for you. This curve is computing that curve for you. And you can actually, if you get the 4 arguments here, it returns 4 values. You can actually see what the thresholds are they used. So the thresholds, let's clear my console. The first 5 thresholds were very high, and the last 5 thresholds will be very low. Last 9. So T stands for threshold, and this will be FPR. Oh, I may have just overwritten my X variable. Yeah, I don't want to do that. So this is going to be FPR. This is going to be TPR. These are going to be my thresholds. And this is a key value called the area under the curve. That's probably the most popular and most, I would still say, most important performance metric for any learning algorithm, because it measures by measuring the area under this curve, and we can plot we can put in the title. Well, is it really 1? I don't believe that. Yeah. 0.9956. So the area under the curve, oftentimes it matches the accuracy, but not always. And so here the area under the curve is very high. It's 99. So this is a classifier that AUC, area under the curve, is like a measure of the separability of the 2 classes. So if your 2 Gaussians, the data of your 2 classes is very well separated, you have a high area under the curve. Let's see, what else did I want to do here? Oh, right. We haven't interpreted the classifier yet, at all. We fit the function, but we haven't looked at the coefficients of the model. So this is important. So let's make another figure here. Stem B. Okay. Come on, toolbar, go away. And let's actually let's do it like this. So, and let's actually put labels on this. So what can I deduce about, let's actually let's actually try to grab, is there a readme here? Anyways, we'll just do, I wanted to be fancy and put in the string labels for the feature, but let's just skip it. So we know that feature 0 is the intercept. So that's essentially your threshold between like where the decision boundary is. Let's forget about that now. So these are my 9 features here: 1, 2, 3, 4, 5, 6, 7, 9. So what can I say? What is my interpretation of the 9 features that went into the model, and what did the model essentially learn? There's 2 things that when I look at this that kind of jump out to me. Yeah, that's right. First 9 are important, the 2 doesn't matter at all. But there's something else though that should jump out at you about these weights. Yeah, they're all the same sign. So all positive or all negative. It doesn't. Don't worry about the polarity. Just worry about, like, if you made the offset negative and you made all the weights positive, you get the same performance, obviously. So the fact that they're all the same sign tells you that well, how do I do this in words? So in some problems, what you will do is you will subtract one feature from another to get a cancellation effect. You're not doing that at all here. You're literally saying, like, let's say that 1 and 9 were the same height, but everything else was 0. Your classifier would essentially be saying, I'm just going to take clump, I'm going to look at clump thickness and whatever mitosis, whatever that 9th feature was. I'm just going to add those 2 up and I'm going to compare it to a threshold. If it's bigger than that threshold, I'm going to say malignant, and if it's less, then it's benign. So this is literally just a straight up, linear combination. There's no cancellation effects. You're not like, you're not looking. So I think what it means about the data is, it's not, I was going to say is redundant, but that's actually not true. Actually, I would argue that 1, 9 may actually be correlated based on this. We should look at that.
What if you were to think of it as contradictory information?
Yeah.
Or at least one feature.
Yeah, but you know what it is, because it's sort of but keep in mind that some of the measurements could be negative, right? If some of our features were negative, then yeah, so actually it's probably more of a statement that all our measurements are probably all positive numbers. if you were to look at the histogram of all your features, let's actually put this into the code. If you were to look at the histogram of the features, I bet you they're all going to be, it's always dangerous to say, I bet in class, but yeah, so they are all positive, right? And so that's why, right. So, but yeah, so in that case, what you're saying is true. There is no, the features don't, if you were subtracting certain features, then yeah, they would, if you were adding one and subtracting another, then those features would kind of have pointed to different outcomes. One feature would point to benign, the other to malignant. But probably all 9 of these features are, the bigger they are, the more likely it's malignant, essentially.
But Professor, if you were to run this, and like you said before, let's say you get 9 and the other ones didn't really matter, would you then suggest them in another study? You just don't even take those.
Yeah, exactly.
9 features.
That's right. You would just, yeah, especially if there's labor involved, you would
Or you just try to get new ones.
oh yeah, or new, yeah, better features. Yeah, absolutely. I mean, when we there's this technique called L1 regularization where you're telling the algorithm to automatically set many of the weights to 0. And so what that allows you to do is just throw every feature you can think of, and the learning algorithm will tell you which ones are not important automatically. So my hypothesis was that feature 1 and 9 were going to be very strongly related. Actually, that's true. Oh, I've overridden X here. That's the problem. Nah, they're not that correlated, actually. What size of X? I mean, they are significantly correlated, but it's nothing like. So that's actually a good sign for learning them that the two, well, that's weird looking. Can that be right? Yeah, one of them is very, no, they're both very discretized, I guess. Wow. Let's look at a sample row. Let's look at a few examples.
Is this X the original one or the second one? Because it has 2 X's.
Yeah, I know, but I'll run. I think I cleared it. Let me try and run again. Yeah, I got rid of that one at the end. I changed it to FPR. So I think the data is just very. If I do table, I think table X will work. No. If I do look at the features for like the first 10 examples. Yeah, they're very discretized. The data is very discretized. Really, you can't handle 10 columns. Yeah, so your data here is it's very quantized. I guess for all the if I go unique of all of X, are there even? Yeah, so the X values are, yeah, quantized. What I'm saying is this data that comes in, like if you look at it's because a lot of these I think were probably determined subjectively, right?
So the maximum is 1, right?
Yeah, yeah, the maximum is 1. Yeah, so yeah, they probably are normalized actually, but you don't. So okay, this is another, and this is one of these things where it's not in the theory, but it is very important to practice. If you don't normalize your data, sometimes you're like if the scale of the different features is way off, like if one feature has values from 0 to 1,000,000 and another has values from 0 to 1, some learning algorithms can't handle that. Some can, but oftentimes what you'll do is you'll It's called the Z-score on your data before you throw it into your algorithm. But all in all, I think this this is a good data set. What else did I want? Yeah, let me see. Is there any questions about the general, what we did here, the steps we did here? Step one is to, basically assemble collect your data and put it into the form that you need. Step two is to fit a model. And then this is step three here. Use a model to make predictions. I guess step four is evaluate performance. And so we could do something like, last thing I'll do, then I'll let you go, is to replace X with only, make sure this is right, with only the first and the last dimension and see how well it does. So that would be a two-dimensional logistic. Oh, right. That's why you should never hard code anything. Right. So with only two features, you still get very good performance. You get an accuracy of 88% and an area under the curve of 0.93. So keep in mind that this is all trained out. I want to save the discussion about generalization because that deserves its own days probably, because the understanding generalization and machine learning is super important. I don't want to bundle in with this. I want to make what I wanted to show here is just the general pipeline, the general procedure recipe for fitting and evaluating a model. I think what I'll do on Monday is I'll take the same data, we'll load it into Jupyter, and we'll run their version of the logistic and we'll compare performance. And in terms of what we've done, what mnrfit did is it found a W that basically mapped benign X's to a small probability, and it mapped malignant X's to a high probability. And I didn't show it here, but I will try to on the board next week give you guys the intuition for how it actually does this. And that's where maximum likelihood comes in. So there's always, in every learning algorithm is going to have a cost function that is looking to minimize, also called a loss function. So have a good weekend.